Okay, want to talk about a NASA sequential phase two that we're working on, both advanced cooling technologies and with working with astrobotic technology. You can see the authors here. Okay, agenda describe the motivation for why we're looking to do these thermal control devices, the objective to develop a thermal toolbox, discuss then the two devices we're mostly developing right now, loop heat pipes with thermal control valves and two-phase thermal switches, and then talk about some future work. So when the astronauts went to the moon in the 60s and all, they basically went during a very thermally benign time during the lunar early morning. When we go back to the moon, we want to be staying there during the entire lunar day and lunar night. Now, the problem is that um, we have a number of devices that can provide variable thermal links to allow you to dissipate heat during the day and pretty much go down to survival mode during the night. But the problem is they require electrical power to operate. And one calculation says that providing 1 watt over the 14-day long lunar night requires about 5 kilograms of extra solar cells and batteries. So what we're developing here is variable thermal links, which give you high minimal delta T while rejecting heat during the day and passively shut down at night, minimizing the heat losses. So this is just showing a basic thermal management concept with pretty much kind of everything. We have electronics here. We have a thermal switch that disconnects when it gets colder. We have a variable conductance heat pipe with non-condensable gas that opens up during the day to reject heat, and at night the thermal switch disconnects. The variable conductance heat pipe basically shuts down also, and we're providing a little bit of heat from a warm phase change material thermal storage. Now, the requirements for the instrumentation, if you look at Mars or near Earth orbit, you're kind of looking at half a day long night for Mars, 90 minutes for solar for an eclipse, and 200 degrees K nighttime temperatures. Whereas lunar day and lunar night, you have about 400 K during the lunar day, and during the lunar night, you can drop down as cold as 100 K. So some of the missions we're looking at is the NASA Viper rover, currently working on flight hardware using some of these technologies, and some astrobotic lunars and rovers. So our objectives are to develop a high technology readiness level thermal toolbox that we can develop complete thermal control systems for lunar landers and rovers. We have a number of programs in parallel for heat acquisition, heat transport, thermal storage, and heat rejection. I'll have a picture at the end of the presentation that you can take a picture of to get more information on some of the programs we're developing in parallel. Now, currently we're developing 6 components to help enable lunar operation during the lunar night and day. Thermal control valves and a high power thermal switch on this program. 3D printed loop heat pipes we're developing on a separate NASA SBIR. Variable view factor radiators, improved wedge locks for operation in vacuum, and phase change materials in microgravity. The work on this program to date has concentrated on developing the thermal control valve for loop heat pipes and the two-phase thermal switch. Now, in previous work, we had shown that this is a picture of a loop heat pipe. As you know, you put heat in the evaporator wick, you get vapor flow going down into the condenser. The vapor gradually cools and condenses, and then you have colder liquid returning into the compensation and the interior of the evaporator wick. What we have done previously was using a proportional thermal control valve that during the day let most of the vapor flow to the condenser, and a very small amount could return directly. During the lunar night, what happens is, as the thermal control valve gets cold, it sends almost all of the vapor flow back directly to the compensation chamber. And basically, what you're doing is you're short circuiting the pressure difference between the evaporator exterior and the internal compensation chamber and evaporator internals, so the loop P pipe stops operating. Now that actually worked fairly well. We used a thermal control valve designed and manufactured by Pacific Design Technologies. It's a proportional valve in that as the temperature goes up and down, the valve operates over a 20 degrees C temperature range to switches from developing all to one outlet to the normal outlet to the bypass outlet. So these things worked very well. It is TRL9. It's currently used on several pump thermal loops for the Mars Science Laboratory, and I believe one other rover on Mars. One of the problems is it's a proportional valve, so some flow always goes in both directions, and it's actually a fairly complicated valve with very high precision tolerances, 10 thousandths of an inch type of things. So we're looking in this program to develop a simpler, cheaper on-off valve. And when we do that, we have two valves. One is a closed, one cold, so that if it gets too cold, the valve basically just shuts off any vapor flow to the condenser to shut off the loop P pipe. We also have an open one cold valve so that when the valve gets too cold, it opens, and basically you have a short circuit of vapor going from the evaporator to the compensation chamber. This is just showing our schematic of our current experimental apparatus. We have the evaporator, compensation chamber, and then we have some valving here so that we can either put the closed one cold valve into the system or the open one closed valve into the system so that we can determine how the loop heat pipe works with either of the two valves, as well as a control with no valves operating. So this is just showing some experimental works, some simple valve tests. You can see your vapor temperature is staying fairly cold until you get to the set point here, and then the valve opens up and you have vapor passing through. We're also doing a series of endurance tests because these valves, we would like them to operate for several years on the lunar surface. So you have to cycle them back and forth and show that there's no problems. So currently, our current designs, we've cycled them for 4,500 times and found no problems. We're now working on a enhanced design, and once we get that all completed, we'll continue testing in the loop P pipe, as well as do more of these cycle testing. So right now we've basically we're finishing. We should finish developing the thermal control valves by the end of this year, and then we're going to work with Astrobotic to do some testing, first at ACT and then at Astrobotic, and looking at proof pressure testing, performance, and shock and vibration testing. The other device we've been developing recently is what we call a two-phase thermal switch system. Basically, most thermal switches are conduction-based devices, and they're designed typically to transfer a couple watts. So they'll be in contact in one case, let you have a few watts go through and then disconnect when it gets colder and not allow the power to perform. What we're trying to do here is to use a two-phase thermal switch so that rather than 1 to 2 watts, we can talk about maybe transferring a couple hundred watts or something. Same type of thing. You have a heat source supplying heat. The vapor is going up and condensing and draining back down. When the heat source is not sufficient, the system is disconnected. As you apply more power, the vapor pressure goes up, the bellows expands and comes into contact with the heat rejection surface, so you can radiate heat and reject it. So we have built one valve, a simple valve here, just showing it operating. We're trying to get an idea of um, how the valve operates, the thermal resistances we can see, and we also want to see that there's some disagreement between us as to does the valve do a lot at certain in the actuation temperature range? Does the valve tend to just actuate, or does it tend to go on and off a lot of times? And these tests, by measuring the electrical resistivity, will allow us to determine the valve operation so we can feed it back into our computer models of the system. This is just showing some initial test data as the system is working. You have when it comes in contact, you have a lot more temperature going through, and then as you drop the power down here, it will disconnect again and let the temperatures drop. Now, the first place we want to apply the thermal control switch is for a cube rover that Astrobotic is developed. This is a very small rover. It's only dissipating about 7 watts, and you can see the design to the right here. We're looking at a target height of about 1 centimeter. We want to maximize the on-off conductance ratio and minimize the off conductance. So the current design, you have all of the electronics mounted to a radiator plate here. What we've done is put thermal switches in, and then the actual radiator panel we've moved up by about 1 centimeter so that we can make and break the thermal contact between the electronics and the radiator as it gets hotter or colder. This is one design concept with the bellows thermal switch here held in place, and excuse me, we need to keep this very rigid to avoid having the radiator panel deform when the bellows operates. The second design concept is to structurally stiffen the radiator by affixing a heat pipe along the length of the radiator on either the bottom or the top side. What you have here is you have a system with a fairly stiff, so that the bellows will contact the flange of the heat pipe, and then the heat pipe will transfer the heat over the entire um, area of the radiator, and does improve radiator conductivity. Does add some additional mass, but it does solve the problem of deflection. So we're currently building the design shown here. You have an aluminum ammonia screen wick heat pipe here that's acting as the thermal switch. You have the radiator paddle, and we've put the heat pipe on the top of the radiator paddle, so we get a better thermal contact between the thermal switch and the radiator panel. So we're building those right now. Again, we expect to finish that by the end of the year and have this initial testing. We're going to fabricate and validate some test devices with Astrobotic, both a loop heat pipe with thermal control of a thermal control switch. And once we validate those, we're going to do a thermal control design for a lander mission, fabricate and test an engineering design unit for the mission, and do, again, a thermal control design for small rover. The cube rover one I showed earlier is what we're going to base it on, and fabricate and test a complete EDU. And then after that, we'll build flight hardware for a NASA-selected application. Just want to acknowledge this is funded by NASA Sequential Phase 2 SBIR. Jeff Farmers, the technical monitor, and Dave Bugby of NASA JPL has also provided many helpful suggestions. I'd like to thank our technicians for the assistance with fabrication and testing. And finally, if you take a picture of this, you can get a link to showing all of the previous work that we didn't have time to discuss here. So that's it. I can take any questions now.
Yeah, thanks, Bill. That was very, very interesting. We've got some questions in the chat here. Do you expect much variance in loop heat pipe performance spreads from lunar to Mars gravitational environments?
For the loop heat pipes, we don't expect that much difference. We do these systems would also work for like a deep exploration mission where again you're trying to have a variable thermal switch without with passively. Both lunar and Mars loop heat pipes are a really neat device, and that they can operate like a meter against gravity. So you do have to worry a little bit about when you have them in a vertical orientation with the liquid dripping down, but we have some systems to accommodate for that. But in terms of lunar and Mars, it's really a fairly negligible change that they work on Earth also. It's different with the variable conductance heat pipes and all that we're developing separately, where you really have to maintain a kind of orient them so that they are always level or gravity aided, even if they land kind of on a cocked tilt.
Okay, yeah, that makes sense. We got another question in the chat. What value of conductance between the heat source and the radiator do you achieve when this switch is deployed? And this is for the thermal switch.
Can you repeat that?
What's the value of conductance that you achieve when your thermal switch is activated or when it's deployed?
I don't have that right now. We're still actually building them, but we're expecting to have oh, we're more concentrating on the ratio of on off, and we're looking to get something that has an on off ratio of more than 100. 100. That's kind of more important than the actual value. We do have a little bit more extra radiator area, so we can expand or contract the radiator as needed, depending on our results.
Okay, and maybe add more switches, and you can kind of tailor things
Right.
accordingly.
We're like the current design. We're using two switches to get a better performance.
Okay. And is the primary, this is a question for me, is the primary, I guess, mode of heat transfer within the switch, is it through the vapor within inside the switch, or is it through the bellows?
No, well, we're trying to we are trying to basically minimize the heat, the conduction through the enclosure if needed. And right now we're thinking of really not using a sealed enclosure. And the bellows themselves, this is basically a heat pipe. So when it's in contact, you have excellent thermal conductivity because you're doing evaporation and condensation.
Okay. And does gravity play a role and kind of in the same regards to the previous question and how you orient these?
Yes, it does play a role, but what we are assuming is that they were going to be in a gravity aided orientation, so that the, on the moon or Mars or wherever we use them, or in space where we do have a wick to return them. They can operate against gravity by being turned upside down because they're fairly short, but you do have a reduced power when you do that.
Okay, very interesting. And then another question for the thermal switch. What sort of lifetime can you expect from these?
Well, we're expecting to have basically a very long lifetime. We're designing the bellows. We're keeping the travel to a minimum, and we're operating below the fatigue limit. These are steel bellows, so if you're not stressing them very much, the fatigue life is infinite.
Okay, so you're really just sort of elastically deforming it, and as long as you keep it within that range, you don't expect much creep or stress propagation or cracking and forming within there.
We are trying to keep it in the elastic mode and below the stress limit. So we're hoping to have very, very long lifetimes.